The success of animal breeding depends on the success of identifying the genetically best animals so that they can be used as parents to produce the next generation. How can that be achieved? How can the genetically best animals be identified? Let's consider a sheep farmer who wants to select a ram to mate with his ewes. The most important breeding goal of the farmer is to increase the body weight of his sheep. So which ram should he choose? The challenge the farmer faces is how to identify the genetically best ram for breeding. In other words, he needs to get a good impression of the genetic value of the ram as father of the next generation. This is also called the breeding value of an animal. If we would know the breeding values of the rams, we could rank them accordingly and then choose the best ram for breeding. But how can we obtain such a ranking of the animals? To rank the animals, we would need to get an insight in the breeding values of the rams. The problem is that we cannot measure the true breeding value, but we can make an estimate of it. The most basic method of ranking the rams would be by recording their own body weight and rank them accordingly. As the aim is to rank the rams such that the superior animals can be identified, the weight of the individual rams is expressed relative to the average weight of all rams. This way, animals that are heavier than average will obtain a positive value, and animals that are lighter will obtain a negative value. Obviously, given the fact that the farmer wants to increase the weight of his sheep, the interest is in the rams with positive values, and the larger the value, the better. Now we have ranked the rams according to their body weight, and we have determined which ones are better than average and how much. But we still don't know whether this represents the ranking according to the genetic potential or the breeding value of the rams. What should we do to translate these relative performances of the rams into their estimated breeding values? We need to find out how well the recorded body weights represent the genetic potential of the rams. To achieve that, we can make use of the heritability. The heritability of a trait indicates how much of the variation among phenotypes in a population, so in this case body weight, is due to additive genetic differences between the animals in the population, and how much is due to the environment. The heritability is in fact a regression coefficient of the true breeding value of animals on their phenotype, where both are again expressed as deviations from the population average. So, the estimated breeding value equals a regression coefficient times the phenotype, expressed as a deviation from the population average. So, although we do not know the true genetic potential, we can estimate the breeding value, in short EBV, because we know the phenotype and the regression coefficient, which is in this case the heritability. This procedure of using the phenotype and a regression coefficient to estimate the breeding value is the core principle of breeding value estimation. Now, let's go back to our sheep farmer. He is considering using a ram that weighs 90 kilograms, but first he wants to know its estimated breeding value. We know that an average ram in the population weighs 80 kilograms, and the heritability for body weight is 0.45. Because in this case of own performance, the regression coefficient of the true genetic potential of the rams on their phenotype is equal to the heritability, we can estimate the breeding value of the ram as 0.45 times 90 minus 80 is equal to plus 4.5 kilograms. This means that the genetic potential of the ram is estimated to be 4.5 kilograms higher than the population average. Note that the EBV is expressed in units of the trait, in this case in kilograms. Using the same approach, we can estimate the breeding values of each of the rams in the population and rank them accordingly. Some rams will have a negative EBV because their estimated genetic potential is lower than the population average. These rams obviously will not be rams of choice for breeding, given that the breeding goal is to increase the body weight in the next generation. This was quite a simple way to estimate a breeding value, but how accurate is an estimated breeding value? The accuracy largely depends on the heritability of the trait that you want to estimate breeding values for. The higher the heritability of a trait, the better the genetic potential of an animal can be estimated from its phenotype, and the better ranking of animals on their EBVs represents the true genetic ranking of the animals. Unfortunately, for traits of low heritability, it is not so easy to accurately estimate the breeding value of an animal. For such traits, the ranking according to EBV, based on own performance, would not necessarily represent the ranking according to the true breeding value of the animal. To get some insight in this matter, imagine that you could create a plot with a true breeding value on the y-axis and the estimated breeding value on the x-axis. Each EBV is linked to its accompanying true breeding value in a data point. If the EBVs are estimated accurately, the data points will be nicely on a straight line connecting each EBV to the true breeding value of equal size. Unfortunately, it is very rarely the case that breeding values are estimated with such a high accuracy. So why not? Why are we not always able to accurately estimate the breeding value of an animal? We already briefly discussed the role of the heritability. If the heritability is low, then the variation in phenotypes is only for a small proportion due to genetic differences between the animals. So, if we only use the information on the animals themselves to estimate the breeding value, then the variation in EBV also will not only be due to genetic differences among the animals, but also due to environmental circumstances. If you would now create such a plot of the estimated against the true breeding value, the points in your plot will not be on one line, but instead will form a cloud. So what can we do to improve the accuracy of EBV? There are two factors that can be improved: the quality of the phenotypes and the use of information of relatives. We will not go into detail on how to improve phenotype recording, but we will show how we can use information of relatives. For that, we can make use of the fact that related animals share part of their genetic potential. The closer the relationship, the larger the shared part of their genetic potential. So, if we would also know the body weight of the father of the ram, it would help to create a more accurately estimated breeding value for the ram, because the father and the ram share 50% of their genes. If, in addition, we would also know the body weights of 5 brothers of the ram, it would add even more, because the ram and his brothers also share 50% of their genetic information, and body weights of 25 half-brothers again would add, even though the genetic relationship between the ram and his half-brothers is not as strong as with his full brothers, or his father. In other words, not all information is equally valuable. The closer the genetic relationship, the more valuable the information for estimating the breeding value of an animal. However, there is only one father, and there may be multiple brothers, and multiple brothers or sisters are more informative for estimating the genetic potential of an animal than a single parent. But offspring are even more valuable because there can be multiple of them. The more offspring are available, the more accurately we can estimate the breeding value of the animal. If we have information on many offspring, we can even approach the 100% accuracy. Then the EBV becomes equal to the TBV. That would be the ideal situation. As we have seen, not all information is equally valuable for estimating breeding values. How can we account for that when estimating breeding values? The answer is in calculating the regression coefficient. Let's consider the situation where we have information from 10 half-sibs on body weight. Suppose they are 5 kilograms heavier than average. The formula for calculating the regression coefficient is, in this case, therefore, the EBV of the ram based on these half-sibs is. Now we have two EBVs, one based on the own body weight and one based on half-sibs. The question is now whether we can do better than that and combine the information. We should not just sum these two EBVs. The solution is multiple regression. The B values cannot be calculated with the equations in the appendix anymore, because there is an overlap in information. The ram itself and his half-sibs share a quarter of the genes, and we need to account for that in calculating the B values. Therefore, we use an Excel sheet specifically designed to calculate B values in case of multiple regression. With this sheet, the calculated B values are 0.41 for own body weight and 0.33 for the half sibs. So when we fill in those values, we can obtain the EBV of the ram. Generally speaking, the more phenotypic information there is on related animals, the more accurately we can estimate the breeding values. In summary, the success of identifying the genetically best animals depends on the heritability of the trait and on the amount and quality of information we have on the phenotypic performance of the animal and its close relatives. Those factors determine the accuracy of the estimated breeding value. So, the success of animal breeding depends on the collection of good quality data on many animals, obviously in addition to keeping records of genetic relationships between the animals.